Have you ever wondered how your music app just knows all your favorite rock songs? Or how a social network can map out your entire friend group in like a split second? Well, it's not magic. It's actually a pretty simple language that's running our whole digital world. And today, we're going to decode that language by diving into the power of sets and relations. I mean, just think about it for a second. From the contacts in your phone to your grocery list, your brain is constantly, automatically grouping and sorting stuff. But how do computers do it so fast and so well? Well, it all starts with a core idea that you've been using your entire life, probably without even knowing it had a name. So here's our game plan. We're going to start with the absolute basics, the set. Then we'll see how sets can fit inside of each other. After that, we'll build up to the big idea of a relation to connect everything, figure out how to draw these connections, and then finally, we'll uncover why all of this is so important in the tech you use every single day. Okay, let's jump right in. We're starting at the very beginning, the foundation of how we organize pretty much everything, both in our own heads and, in computers. And that is the idea of a set. So what exactly is a set? It's really simple. It's just a collection of unique things. Now, the most important part of that definition is the phrase well-defined. All that means is that for anything in the universe, you have to be able to say it with 100% certainty. Yep, that's in the set. Or, nope, it's not. There's no maybe, no gray area. And we've got two main ways to talk about a set. The first one is super straightforward. You just list everything in it. Like here for set A, you just write out 1, 3, 5, 7, 9. The other way is to just state a rule that everything in the set has to follow, like all odd counting numbers less than 10. The cool thing is, both of these methods are describing the exact same group of numbers. Now, this is a really important little detail. Equal sets mean they have the exact same stuff in them. That's it. The order you list them in makes no difference. But equivalent sets are different. They just have to have the same number of things. The things themselves can be totally different. So think about it like this. Your two hands are equivalent sets. They both have 5 fingers. But they're not equal sets because, one's a left hand and one's a right hand. Okay, so we've got these collections called sets, but things get really cool when we start looking at how these collections can actually fit inside of one another. The idea of a subset is actually so simple. If you can take every single item from set A and find it hiding somewhere inside set B, then boom, A is a subset of B. It's just a set inside another set. Let's look at this example right here. Set A has 33, 66, and 99. Now, if you look over at set B, yep, you can spot all 3 of those numbers in there too. And that's all it takes. A is officially a subset of B, and we use that little symbol there to show it. Okay, but we can get even more specific. That regular subset symbol is kind of like saying less than or equal to. The sets could be exactly the same, but a proper subset, that's like saying strictly less than. It means that the bigger set, set B, absolutely must have at least one extra thing in it that set A doesn't. And here are 2 golden rules that are always, always true. First, any set is a subset of itself. That makes sense, right? All the elements are definitely in there. And second, the empty set, that's a set with literally nothing in it, is considered a subset of every single set that exists. It's a weird one, but it's a super important rule. All right, we've got sets, we've got subsets. Now we get to the really good stuff, using all this to build connections between the elements. This is where we finally get to define what a relation is. This quote here really hits the nail on the head. A relation isn't some scary, complicated math problem. It's just a way of saying, hey, this thing from the first group is connected to that thing from the second group because they follow a certain rule. That's it. Okay, I know. This formal definition looks a little intense, but don't worry, let's just break it down real quick. Ordered pairs just means we're linking one item from set A to one from set B, and A times B, that's just the fancy name for all the possible pairs you could ever make. A relation is simply a hand-picked selection, a subset of those possible pairings. See? Once you strip away all that jargon, that's all it is. A relation is nothing more than a list of pairs. You take an item from the first set, an item from the second, and if they follow your rule, you pair them up. That final list of successful pairs, that is the relation. Let's actually walk through this one. So our rule is same parity. That just means both numbers have to be even or both have to be odd. Let's start with the number 1 from set A. It's odd. So we look at set B and find the odd numbers, 1 and 3. That gives us our first two pairs, 1, 1 and 1, 3. Next, let's take 2 from set A. It's even. In set B, 2 and 4 are even, so we get the pairs 2, 2 and 2, 4. You just keep doing that for everything in set A, and this whole big list of pairs you end up with, that's our relation. Now, a long list of pairs is fine, I guess, but it's not exactly easy to understand at a glance. Luckily, there's a much more intuitive way to see these connections, by actually drawing them. We can use something called an arrow graph to see what's going on. This simple little trick turns that boring, abstract list of pairs into a clear map of connections that our brains can process way, way easier. So let's build one right now. Let's say our first set is a group of students, and our second set is a list of available courses. The rule that connects them, the relation, is simply is enrolled in. And making this graph is incredibly simple. You just put a dot for every student on the left and a dot for every course on the right. Then, for every single student course pair in your relation, you just draw an arrow pointing from the student to the course they're taking. That's literally all there is to it. So we can define connections, and we can draw them. But now we get to the most important part of all. Why should you care? Let's take a look at how this abstract idea is actually powering our modern world. This is always the big question, right? It's the one you're probably thinking, okay, this is kind of neat, but where does this stuff actually show up in real life? Well, the answer might just surprise you. The truth is, this isn't just theory. It is everywhere. The relationship is friends with on your favorite social media app. That's a relation. All that customer bought this product data for online shopping, that's a relation. The giant databases that connect every employee ID to their department, it is all built on this simple idea of pairing things up based on a rule. This really is the hidden architecture behind our digital lives. So the next time your phone suggests a new friend or your music app builds you the perfect playlist, you'll know the secret. It's all just sets and relations working behind the scenes. So I'll leave you with this to think about. What hidden connections in your own life could you map out with just a simple set of arrows? Thanks for joining me.